Hi everyone, and welcome to the Chapter 5 lecture on z-scores. So far, we've only described distributions, but now it's time to describe a single score's location in a distribution using what's called a z-score. And this is important because numbers without context are essentially meaningless. If you were to score 350 points in a class, is that good or is that bad? It really reminds me of this meme from Doctor Who, asking if 4 is a lot. It really depends on what we're measuring here. Essentially, if we can identify a mean, we can create a point of reference for ourselves and provide context to the number. Let's use this example. Someone scores a 26 on a leadership test. Is that a high score or a low score? Well, if we know that the mean score is 20, we can say that this person scored above the mean. They might be a more skilled leader compared to others who took the test. However, knowing the standard deviation is helpful here as well. If the standard deviation is 3, a person with a score of 26 is 2 standard deviations above the mean. The standard deviation acts as a unit of measurement to know how extreme the score is. Now, let's look at this example. Say the same person takes a test on planning ability and they score an 84. That sounds pretty high, right? Especially when their last score was a 26. But if the mean score is 90 and the standard deviation is 12 for this test, this person has scored half a standard deviation below the mean. They are slightly below others who took the same test. So at this point, we have two different tests which are measured on two different scales. By using z-scores, the number of standard deviations above or below the mean, we can say that this person is slightly higher than average on leadership and slightly lower than average on planning. And note that we are making these measurements consistent across groups by making the mean be 0 and counting 1, 2, 3, and so on in either direction. This is what gives us that point of reference and allows for these comparisons to be made. There are other examples of this out there. Maybe you take the SAT and your friend takes the ACT and you want to compare your scores. Or maybe you're a clinical psychologist and want to evaluate depression and anxiety scores in a patient. This method of standardization allows you to do that. So how do we calculate z-scores? We have a different notation for both the population and the sample, but the math is the same. For the population, we have x, which is the individual score, minus mu, the population mean, divided by sigma, the population standard deviation. For the sample, we have the score minus the sample mean divided by the sample standard deviation. And just like before, you would base the notation on what the problem tells you. So let's go back to that example we were using, examining leadership and planning, and figure out how we arrived at those z-scores. Let's say that these are both samples and only select people participated in taking the surveys. Starting with leadership, the person we were interested in scored a 26. The mean was 20 and the standard deviation was 3. Pulling up that sample z-score equation, we would just plug in the numbers. That would give us 26 minus 20 divided by 3. This reduces to 6 divided by 3, which gives us 2. The interpretation of the score is that this person is 2 standard deviations above the mean. For planning, that same person scored an 84. There was a mean of 90 and a standard deviation of 12. Using that same equation, we would just plug in the numbers and we would get 84 minus 90 divided by 12, or negative 6 divided by 12, and this gives us negative 0.5. Because it is negative, this person is half a standard deviation below the mean. Here are two practice problems for you to try. Pause to solve. The answer will be shown in 5 seconds. So for the first problem, we have a score of 40, a mean of 65, and a standard deviation of 10. As you can see, the statistics provided are for the sample notation. So pulling up that equation, we have 40 minus 65 divided by 10, and that gives us negative 2.5. For the second problem, we have a score of 425, a mean of 350, and a standard deviation of 25. Hopefully you've noticed that this is a population notation, so using that equation, we have 425 minus 350 divided by 25, and that gives us 3. We can also work backwards. If we are given a z-score, we can use the same statistics in a different order to find the raw score. The raw score is just another term for that individual score we talked about earlier. Again, we have different notations for the population and sample, but we calculate the raw score in the same way. For the population, the raw score is the z-score multiplied by the population standard deviation plus the population mean. Likewise, for the sample, the raw score is the z-score times the sample standard deviation plus the sample mean. So let's try this problem. We have a z-score of -1, a sample mean of 100, and a sample standard deviation of 15. Using that sample notation, we just plug in the numbers, and that gives us -1 times 15 plus 100. Simplifying this, we have -15 plus 100, which is 85. So our raw score is 85. Let's try another problem, this time using the population statistics. We have a z-score of 4, a population mean of 50, and a population standard deviation of 12. Using the population equation, we have 4 times 12 plus 50, which is 48 plus 50. Therefore, our raw score is 98. Here are 2 problems for you to solve on your own. Pause to solve. The answer will be shown in 5 seconds. Okay, so for the first question, we have population statistics with a z-score of 2.5, a mean of 20, and a standard deviation of 18. So we would use a population equation. 2.5 times 18 plus 20 is 65. For the second problem, we would use the sample equation. We have a z-score of -2, a mean of 50, and a standard deviation of 10. So -2 times 10 plus 50 is 30. And that is all I have for you. If you have any questions, please let me know.